So let us start from the point where we finished in the last class. So if you remember, we were looking at corrections to the leading scattering, to the leading matrix element for the decay process of a real scalar particle to the electron-positron pair, and we were looking at corrections to that leading matrix element. So we found that the corrections will come at third order in perturbation theory, and one such diagrams will be of this form. One of those diagrams will be of this form. And today, let us calculate this diagram. তোমরা এখন আর ক্লাসে নাও আসতে পারো, বুঝেছো? অনলাইনই করো, কারণ এখন see the situation again becoming very, so you try to do it from your hostel. Okay, so let us calculate this diagram. So since this is a diagram at third order in perturbation theory, so we will have this minus I whole cube for each vertex, and now there are, remember the final rules for in the position space, which says that for each vertex you have to put a factor of this minus I times the coupling constant involved in the interaction, and then there will be integration over the space time. So if I call this as x1, x2, x3, so let me call this as x1, x2, and x3. If we call this like this, so these are the three vertices, and there will be integrations over those vertices. So this is one of the Feynman rule. Then we have a scalar field propagator, and that is nothing but I delta f, x2, x3, and then we have electron is getting created at its position at x1. So you can write this down as psi. If I call this psi beta, remember that this was the expression that we got. Psi bar alpha x1. There was a contraction, and this is nothing but I s f. This is the Fermionic propagator beta alpha x2 x1. And then we also had psi alpha x1 times psi alpha x1, is this, and then psi bar gamma. And then there is the contraction, and this is alpha gamma x1 minus x3. Beta alpha beta x1 minus x3, and then we have the external lines. If you remember, for the real scalar field, real scalar particle have nk times e to the power minus I k dot x1 times for these we will have for this external line and this external line for the electron and positron we will have np u bar is p e to the power of minus I p dot x2 and then this equation of positron at x3 is using p s minus p prime this is what we shall have. And obviously there will be indices. So let us also put the indices carefully. This is beta. This is gamma. That is what we have. Okay. So is this clear? So I hope this is clear. So this is quite straightforward. You have to put this coupling constant at each of these three vertices. Then integrations over the vertices x1, x2, x3. And then you have a propagator, I delta x2 minus x3. This propagator for the scalar particle. And then you have the propagators for the fermionic, for these fermions. So there are two propagators. One will be psi x2, psi bar alpha x1. So this is a contraction. So this gives you the fermionic propagator. And this is the other fermion propagator, and then these are the things for the external lines. So now what we shall do is once we have applied the rules for the final rules in the position space, what we now need to do is the following. We shall now move on to the momentum space. And to do that, take this term and let us Fourier transform it. This is 41 I delta f 1 power of minus I minus 60. So this is the Fourier transform of this. And then we also need to put the Fourier transforms of these two propagators. So if you do that, this as before 2 5 4 beta alpha x1, and then there is only one Fourier transform there. This is for this one. We call that momentum Q. So this is what we shall have times all the other factors that are written down here times all these factors. So now what we need to do is the following. We need to perform the x integrals. So this is the before Q1, before Q2, before Q3, you can keep integrals outside. So 12. That is I delta F 1 I Z delta 2 times I Z alpha times Q3. That is what we have. And then we have these factors. So this will be MP in A E in rank. Then we have U class S beta V and 1. We have written down everything, all the factors which do not involve the position, so that we have written down. Now, our aim is to perform the integrals. So let us see what is the x3 integral. So x3 integral is like the ix3 common, then we shall get following. What shall we get? We shall get a star I'm writing x3. So x3 is a, and there is another. There is no x3 here. There is only x3 here. So this will be what? This will be a plus, right? A plus q3. Then e to the power of I. There is another term. Which one? Plus b prime. I missed it, right? Yes, yes. You are correct. There is a factor here plus b prime. Coming from this factor. Now x2, what do we have? We have minus k, x2, then minus q, and then plus p. Then e to the power of I, x1, x1 is q2 minus q3 minus p. So you can see that each of these integrals can be performed, and it will give you this factor of 2 pi whole 4 and Dirac delta functions. So 2 pi whole 4, you will have 3 2 pi whole 4. So what we shall do is, we shall keep one and keep one here. So keep one here. We shall not cancel that. this will lead to, apart from the factors, this will be delta 4 A plus minus 3 A plus minus C A plus A3 plus plus. So once we have this, now we have to perform the delta function integrations over, that is the integrals over the momentum. So what we shall do, as I have done in my calculation, I will first do the integration over Q2. So let me first do this integration. So if we do the integration over Q2, then we see that from this Dirac delta function, two-dimensional Dirac delta function, we have Q2 is basically K plus Q3. So we can get rid of this Q2 and replace Q2 by K plus Q3. This becomes K plus K. There's no problem here. This is done. And Q2, we have to replace K by K plus Q3 here also. So I think I got something wrong. Let me just check. What are the delta functions? Q2 K plus Q3 minus Q2. Did we have that term? K plus Q3. So Q2 is K plus Q3. So this one is correct. Q1 plus Q2. The other one. Q1 plus Q2 minus P. Okay, so this one is wrong. And P prime plus.
So can you show us the other board?
Yes, I'll show you the full board now. You can see the full board. P prime is what? P prime is K. This one is P prime Q3 plus Q1. Where did I get that? X1. Put X1 in. X1 into X. Oh, I made a mistake here. So, see, the mistake is the following. This one will be Q1. This is not Q. Wrong. This one will be Q1. This one is Q1, this is Q2, this is Q3. Just correct this one. This is not K, this cannot be K, this is Q1, right? Okay. So if that is Q1, then you have to be careful. Let me write down the implications once again. So while Fourier transforming, I made an error here. This is the integration over Q1, so this will be Q1. So the first thing I got it right, this one was correct. So this is basically integral before x1 e to the power I, writing all the x1 terms. So x1 term, I will get something from here, which is minus k, which is this term. And then another x1 is plus q2. which is from this term plus Q2 and then minus Q3. So that actually fixes, that actually gives us a direct delta and times F5 over to the power of 4, which I have taken care of. So this gives us K plus Q3 minus Q2. So that is basically, so we replace, we are doing a Q2 integral, so Q2 is basically K plus Q3. So just remember that Q2 is equal to K plus Q3. And then the integration over, so this gives you an integration over Dirac delta function K, Q2, Q2 and Q3. And when you perform the Q2 integral, Q2 becomes K plus Q3. So this one is gone. And the other integrals, they basically give us delta 4. This is for x2. This is for the x2 integral. So from the x2 integral, what we shall have is minus q1. Huh?
You should take minus I4.
This one?
You should take minus I4. Minus.
Whatever, you can take whatever. It doesn't matter. There is no, in Dirac delta function, you can take whatever form. It doesn't matter. You will get the same answer because it is symmetric. So x2, I am taking minus q1 minus q2. So this gives you minus q2. From this term, there is no x2 there. x2
Q3. There will be another Q3.
Which one?
Q3.
I am writing it. This is for the second term. This is for the x2 integral. I am writing the other. So delta 4, the x, now I am writing down the x3 term. x3 we will have plus q1. Then we will have minus q3, and then plus q1. Is correct? So Q2 I have already replaced it by K plus Q3, and here we have to replace it. Q2 is K plus Q3. So what we shall have is, let me actually this form. Q1 plus Q2. Q2 is K plus Q3 minus P. This is what we have. And here there is nothing to replace. So you get this. Fine. Let me just check it. So this gives you the integration over this one. So after integrating, what we have is it's done in a very convoluted way. I have to just figure it out. Delta 4k plus q3 that I have done. So q3 is done. Once you do q2, then the integrations are before q1, before this I delta q1 p delta 4 p prime. I don't know why I got that sign wrong. Check. The last integral I got a wrong sign. Let me just check. It's C, so Q3. So this will be plus. This will be plus. This is plus. This is Q1. And then we have the P prime. This. So everything is plus, so that is correct. This one is correct. And then we have Q1 plus Q2 minus P and K plus Q3. So that I have performed. Q2 is done. So after that we get Q1 plus K Q3 minus K. Fine. Now what we shall do is, let us, I think we are, in my calculation I have performed the Q3 integral. So let us do the Q3 integral. let us do this one. So we can do this one. So this actually tells us that Q3 is equal to minus Q1. This one is also done. So Q3 is done. So what we have to do is replace Q3 by minus Q1 minus Q2. To do that, so this will give us minus Q1 minus Q prime, and Q3 is minus Q1 minus Q prime. Q1 and Q1 gets cancelled, and therefore now we can write this down as, so let me just zoom this part of the board once again. So what we have is minus Ig to Q 2pi/4. See, this Dirac delta function does not involve any Q1, so you can take it outside the Q1 integral. This actually gives us delta 4 A minus B. This is taken care of. All the integrations are done. So now we have an integral P4 over Q1 5/4. Then we have this one, propagator I delta is 1. Then we have I is a minus Q1 minus P prime. This is also taken care of. And Q3, we have to replace here also Q3 by this one. This Q3 is basically minus Q1 right to make this plus. Right? Because delta minus x, the propagator is minus x is basically plus of x. So Q3 here was minus Q1 minus P prime, so we replaced it and then we plus. We have I is F Q1 plus prime, and then what we have is all these factors. Nk you can put it outside. Nk, Np, Np prime, everything goes outside. This factor and this factor also goes outside. So we have 2 bar S beta P. So let me write it in this way, nice way. So I'm writing Q bar S beta alpha, and this one is SF alpha gamma. And then we have 3 S prime gamma. Let me just check whether I've got everything correct. U bar is beta I P, the first propagator. E is so this is done, and this one is
There will be an extra B term, I guess.
which term? Just 1 minute. So I'm coming back to you. Let me go
Okay. Okay.
all the factors, then I'm coming back to you. So P prime is what? P prime is A minus, okay. So what did you say? Let's repeat once more.
Sir, Vs prime gamma P prime term will be there, I think.
I've written it.
Okay, okay. It was not visible, sir. Okay, sir.
Okay, no, I will write it in a clean way, but I will write the result in a neat way now. So what we have obtained is the following: minus ig whole cube 2 pi whole to the power 4 delta 4. This is k minus t minus t prime, and then we have these factors. So I've written we have nk, np, np prime. Now comes the important thing. Now you see that what we shall do. Huh? I will write it. I will write it. Just write it. We'll put this here. Now what I shall do is, I shall just, since this is a dummy variable, I shall just call that q. Shall replace q1 by q. This becomes d4 q by 2 pi whole to the power 4. Then I have I delta f. You can see that I delta f q1, so this becomes q. Now I shall write this down. This is beta. So this is what we wanted. But you can, you are right, you can keep it outside the integral, but I am just you can keep it anywhere. But I shall write in a particular order that is quite instructive. Now I have SF, beta, alpha. Now here I should do one thing. So first of all, Q1 is Q, right? And K is what? K is basically P plus P prime, right? So you can keep it in that form. It is not necessary to do this. But if you do it, you will get the following thing. Since K is P plus P prime, and that factor is K minus Q minus P prime. So what I am doing is I am replacing K by these factors. If you do it, it is not necessary. If you like, you can do it. If you don't like, you can just skip it. Not important. So what this does, you can put K, the value of K over here. What this does is it cancels this P prime factor. And then we have this as P minus Q. So earlier, what was happening is that, see, this Q is basically the loop momentum. Okay, so this will always be there. But there are two additional momentum. But now this is compact. Loop momentum is always there, but only one momentum is there if you use that. So that just makes life a little bit simple. That is why I write it in this way. Then I have I SF alpha gamma. And here also I do, so Q1 plus P prime. So you can keep it in that way, or like Q plus P prime. I think it is better to keep it in this way. Q plus P prime. Then we have P S prime gamma. Sit. So this is the final result. Can you see? Is it visible to everyone online?
Yes, sir.
Yes, Professor.
So now you can see that this is basically the expression for, let me just remove this x1, h2, xt now. So this is basically the expression for this diagram, the mathematical expression for this diagram. We started out by writing down the mathematical expression for this diagram using the Feynman rules in position space that we already know. And then if you Fourier transform it, you have written down the expression in momentum space, and you could have already written down this expression by using the rules in momentum space. You can see this in a very nice form. For the rules in the momentum space are the following. For each vertex, you have a factor of minus ig, so that you do minus ig whole cube, 2 pi whole to the power of 4 delta 4 k minus t prime. That is the overall for momentum conservation. So that this comes from the overall momentum conservation. Then you have these external line factors that you have for these particles, the external particles, these normalization factors nk, np, np prime. That's it. Everything is taken care of, the vertices and the external lines. And then you have a loop, which is not a fermion loop in this case. So this loop tells you that there will be a loop momentum before q, there will be a loop integral before q by 2 pi to the power of 4. That is the Feynman rule for loops. Inside the loop, we have this, the scalar field propagator, I delta q. So if I say that this is the way the loop momentum circulates inside the loop, so we have I delta f q, and then again we have to start from the external lines, because we had only taken care of these normalization factors, but there are these factors, the spin-out factors. So you have u bar s beta. So I'm calling this as beta. This vertex as beta. So u bar s beta momentum p. Then we have the fermion propagator. So it is written in this form, in a nice matrix form: u bar s beta I beta alpha, alpha gamma, and gain z gamma. So now it is in a nice matrix form, and this thing is I SF P minus Q. This propagator is P minus Q, so its momentum is P minus Q. And this propagator that we have here, its momentum is Q plus P prime, and then it ends with P. So you could have written it from the starting point. So if this is K, and you call this as loop momentum Q, so you could have calculated what this momentum should be. So from there you can actually write down these arguments. I think it is easy to see, so let me just check. P.
Can you just repeat the last line?
Just a minute. P. I call this as Q, say. So this is Q, and this is P. So both are, so something coming in, some going out, going out. So what should be this momentum? P plus Q minus P Q. I call this momentum as P plus 1. Or call this as matter. So what we have is going out, so minus P coming in plus Q coming in plus. So this gives us equal to this. So did you follow? This was my last statement. Did you follow? Follow, yes or no? Yes. So what I did was,
Minus P plus Q plus K, right, sir?
which one?
The above that you wrote, minus P plus Q plus K equals to 0.
No. What I wanted to show you is that you could have written down this expression directly by using the Feynman rules in momentum space.
Okay.
So as I mentioned that this part is very clear. Then you will obviously have this part. This is also a part of the external particle, and this is also a part of the external particle. But we have written it in such a way so that it looks like it is in a nice matrix form, right? So now you can get rid of this indices beta and all that. So that is why we started from U bar, then the propagator, and then it ends with V. What is important is that when you write down the expression of the loop, you have a loop momentum before Q by whole 4, and then you have inside the loop you have a scalar field propagator, which is simple to write, this I delta F Q. But what about the momentum of these fermion lines? What about the momentum of these fermion lines? So that you can calculate by looking at this diagram. So what I did was that if I call this momentum as plus Q, if this is plus Q, and my convention, you can take any convention, whatever momentum falls into a vertex, you call that a plus. And whatever goes outside the vertex is going away from the vertex, you call it to be a minus. So there is a momentum that is falling in, so that I call as this one, as this thing. So this is plus this plus Q, minus P is going out from this. So this momentum is basically P minus Q. And therefore, the argument of this propagator is P minus Q. So that is what I did. And you can similarly now you can estimate what this is. This one will be what? This Q is going away, so this is minus Q. So here also P prime is going away, so it will be minus P prime. This is also going away, so if I call this as which one? Y plus P prime. This is minus P prime falling here. So let me do the convention once again. So everything going outside is minus Q. So this is minus Q. So minus P prime is falling inside. Plus minus. It's minus P prime. Minus P prime falling inside means plus P prime going outside. And my convention is going outside is minus. So that gives you minus P prime. And this momentum that is going in this direction, so this is again going outside. So let me call that minus going outside. So this one is therefore minus Q minus because this is going out in this way, but that comes with a negative sense. That means it is something. So that is how you can fix the momentum, the argument of these fermion propagators, the momentum arguments of these fermion propagators. You have to just calculate it by using this momentum distribution at each of the vertices. So this is something like Kirchhoff's law that we use in current electricity. So this is how you can write down the expression of a particular Feynman diagram straight away in the momentum space. And now what remains, that is a separate story. What remains is to calculate these loop integrals. That is a separate story. We are not calculating the loop integrals, but in principle you can calculate these loop integrals. Then, okay. So this is one of the diagrams, and another diagram I want to show you another diagram, calculation of another diagram, and that is this. So this is also a long process that do it systematically. We shall again do it from the first principles by using the Feynman rules in position space and then Fourier transforming it and then getting the expression in momentum space, but it will take some time. We'll do it on Wednesday. So if you have any questions, please you can ask me at this point.
Sir, for the harmonic propagator, SF A equals to SF minus A, right? I mean,
Is it?
inside the bracket. I mean, inside the bracket, it is symmetric with respect to sign change.
Yes, yes.
Okay, sir.
So what is important is that for the vertex, you have the rules, you have the overall momentum conservation that is also associated with the vertex rule in momentum space. Then you have the normalization factors for the external lines, and also for Fermi also you have the spinor factors for the external lines. And then when you have a loop, the loop comes with the loop momentum before Q by 2 pi. And then you put all the internal lines that you have inside the loop. These will be nothing but propagators. So there is one scalar field propagator, two fermionic field propagators, and the arguments of those fermionic field propagators you have to fix it by looking at the conservation of momentum at each of the vertices. Once you do that, you will get the argument of this fermion propagators. So our next task is to calculate this diagram. We shall do it in the on Wednesday. So let us conclude it here. Once we finished calculating this diagram, then we shall move on to QED.
Sir, can you share the recorded lectures?
I can send, but now it is a little bit difficult because I have to send it by email. By email, it becomes very difficult. It cannot be sent to you by email. But once you come, don't worry. I shall put them on YouTube. I shall upload them very soon on YouTube.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Sir,
Ah.
I have a question.
Yes. Yes.
So in the perturbation, we can go up to whatever order we want.
Yes.
So in a particular process that is happening in all the ways, I mean, we can consider first order, second order. So if we see a particular process, how can we say that particular in which way that process has occurred? Or there is some probability that the higher order we go in perturbation, that those processes are less likely to occur.
No. See, these processes are occurring. There is no doubt that this process and this process. Suppose you are in up to third order in perturbation theory, you are working up to third order, then these processes are definitely occurring. But you know that the probability amplitudes for these, when we are calculating a matrix element in quantum mechanics, we are basically calculating the probability amplitudes. And these probability amplitudes are actually smaller than the leading time. This is the standard rule in perturbation theory. Since what we are saying is that perturbation theory holds here, and therefore the contribution of these diagrams to the leading order terms, to the vertex for this decay process will be much smaller than the leading order term that we calculate. So these terms are basically corrections to those terms, and you can calculate the lifetime very accurately to any order, to as accurate. So as you move on higher and higher orders in perturbation theory, your result for the lifetime will be more and more accurate. By accuracy, I mean that it will match the experimental value that the experimentalist measures in the laboratory. So the theoretical value will be very close to that experimental value. Suppose the experimentalist tells you that the lifetime is, say, for this particular decay process is say 9 seconds, or say he says that the lifetime is 9.0234 seconds. So he gives you a lifetime up to 4 orders after the decimal place. And then if you calculate the leading order term, the contribution from the leading order term, from that term if you calculate the lifetime, you may get the lifetime to be 9 seconds. So what about the other 4 decimals, other digits that appear after the decimal place? That you cannot explain by your calculation. So what you have to do, you have to go to higher order in perturbation. And if you take those terms and if you see that your result is matching very closely to the experimental health, then you are happy. Then you say that perturbation theory is working. Okay.
Okay, sir.